I will begin. I wonder how many much memory do I have left? 3 hours and 53 minutes. I think we should be okay. So it's probably enough for the semester at this point. Anyway, I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day and this opportunity just to study your creation again, Lord. Just bless our work today, Lord. In your name I pray. Amen. Okay, so I'll start out by reminding us what was the definition of L1 functions, right? And you remember the have our cake and eat it too. We want to think of them as functions, but they're really equivalence classes, right? Because the almost everywhere issue forbids 0 being the only thing with norm 0, right? So the come on. We had talking about a function from RD, and I think generally speaking at this point they're thinking about it being complex valued, honestly. But this is the norm of f in L1 RD is equal to the Lebesgue integral over RD of this dx. So the set of all equivalence classes of such functions, such that quote-unquote norm, L1 norm, is, finite, that's said to form, that puts f in, we'll find the equivalence class containing f is an element of L1. But as we quibbled over last time, basically this abuse is rampant, all right, that the equivalence class is the function. And we cited some properties of the L1 norm, right? What were the properties of the L1 norm? So, and I'm just going to abbreviate it sub 1 rather than writing L1 RD every time because it gets really old really fast. So if I have like a constant times f, it's equal to the absolute value of the constant times the length of f. And that's for all a in the complex numbers. So there you go. There's explicit evidence he's thinking about complex valued functions. The one norm of f plus g is less than or equal to the one norm of f plus the one norm of g. Of course, this is our beloved triangle inequality. 3, the norm of f in the one norm is equal to 0 if and only if this is equal to 0, which we could write more concretely in terms of functions, f is equal to 0 almost everywhere, right? So we can either say that the equivalence class is just straight the 0 class, or we could say that the function's 0 almost everywhere. And then we also defined a distance function. The distance between two functions, distance from f to g, is the length of the displacement from f to g. So the length of f minus g in the one norm. And so you can prove various things about the distance function. D is for distance, right? And I would say this is the one norm distance for what it's worth. Because, of course, there are other notions of distance we'll talk about shortly. And, all right, so among other things, this is true. The distance from f to g is less than or equal to the distance from f to h plus the distance from h to g, right? So the distance function also satisfies this triangle inequality, right? I mean, the distance function is what's called a metric, right? As you study functional analysis, you'll study a space with a metric more formally. A metric is a a distance function. It's something that's symmetric in its inputs. It satisfies the triangle inequality. And what else? What's that? Yeah, symmetric. So d of fg is equal to d of gf. I mean, that's true for this, but triangle inequality, there's something else that an abstract metric has to satisfy, though. Right, yeah, and the distance, yeah, the distance from x, let's see, how can I say this? Yeah, if and only is, it's the positive definite property. Yeah, so the distance from x to y is equal to 0 if and only if x is equal to y, right? And I think I also need that the distance is positive, right? We shouldn't have that the distance from x to y is like -2. That'd be weird. Okay. Which is part of the abuse in physics when they talk about Minkowski distance or something like that. I mean, the usage varies, though. Usually things, they'll talk about quote-unquote metrics which allow null vectors, like you have a vector which is non-zero and yet has length 0. This is commonplace in relativity. Those are light rays. But anyway, I'm getting way off track. Okay, so that's the distance function, and then complete a vector space V with a distance function D is complete. What's that mean? Yeah, Cauchy, which would be something like xk such that the distance from xm, xn goes to 0 as mn goes to infinity. That would be Cauchy. So it's complete if Cauchy implies converges. In other words, the distance from xn to, say, x star goes to 0 as xn goes to x star. That's not what I mean. N goes to infinity. So yeah, Cauchy implies converge, makes V a complete space. And so the theorem that I am not going to prove, but is proved on page 70 of Princeton Lectures in Analysis, Volume 3, by Stein and Chakrachi, is the Riesz-Fischer theorem, Theorem 2.2. And it says that the vector space L1, and for some reason, he's got L1 RD on like 1,000 things in this section. Like he's got L1 RD as like a subscript for norms. But in the statement of this theorem, even though the text hangs over to the next line, we cannot afford this. Come on. Maybe there's some sort of more nuanced use of the word, just the symbol L1 in here. Come on, editor, do your job. Sorry. Vector space L1 RD, the vector space L1 RD is complete. In its metric. In other words, the metric that was given over here. And again, this is the Riesz-Fischer. Can't spell. F-I-S-C-H-E-R. And then we also have some other nice results. Let's see here. For example, the following families of functions are dense in L1 RD. Simple functions, the step functions, continuous functions of step compact support. These are dense in L1 RD. Now, past this point, he talks about invariance properties and then derives some things about convolution, which I thought I would talk about, but on further reflection, I realize that's too big a bite for me to chew today. Like I can't say just a little bit about Fourier analysis. I don't think it's possible. I'm going to try to say something at the end, but I will not be seduced into those technical details at the moment. All right. So then chapter 3 happens with all kinds of really neat results, which are basically the generalizations of fundamental theorem of calculus and things like that for measure theory. Here, I'll read one. Come on, where'd you go? Let's see here. You know, it has a variety of things. I mean, it has the sort of analog of the, I guess it's kind of sort of like FTC 1. The limit over, if you take a set and it regularly shrinks to x bar and you divide by the measure of that, right? And then you take the integral over u alpha of f of y dy, then you get f of x bar, where x bar is the point where this set is sort of shrinking to. So that kind of resembles the derivative of the integral with a bound. It gives you back the function evaluated at the bound which you're varying. It's sort of corollary 1.7 in some sense resembles FTC 1 from one perspective. I don't know. And then his anyway, I think it's an interesting chapter, chapter 3. I don't think, as I read through it, you know, a few months ago when I was thinking about doing this, as I was reading it before, I didn't feel like I would have necessarily personally thought of these theorems. I mean, they're not. Okay, so you take complex analysis and you see how the fundamental theorem of calculus generalizes for complex analysis. It's completely unsurprising. I mean, it's almost literally the same thing. What's the, you know, FTC for if you have a complex function and it happens to have an antiderivative and you're looking at a curve that goes from one point to another, the integral in the complex sense is f of the endpoint minus f of the starting point for your antiderivative f, right? And there is something in here that's kind of like that, but fundamental theorem of vector calculus. Well, I'm not talking about the line integral. I'm talking about the complex, the contour integral. What I'm trying to say is I found the theorems in complex analysis much more unsurprising. Some of the things in this chapter, maybe it's just my naivete in terms of measure theory at the moment, but I don't know. Chapter 3 is interesting, but we must go on. So, Hilbert space, yes. So chapter 4, just because I want to at least give you at least a brief introduction to these ideas and some of their most important structures. So, let's see here. This is what Plancherel said in 1912. Born barely 10 years ago, the theory of integral equations has attracted wide attention as much as for its inherent interest as for its importance of its I can't even read, for the importance of its applications. Several of its results are already classic, and no one doubts that in a few years every course in analysis will devote a chapter to it. Yeah, he's not wrong. Let's see here. So, Hilbert space L2. Let's talk about this here. He said a prime example of the Hilbert space is the collection of square integrable functions. So this time we're going to look at functions again from here to here. But this time we want, and we're going to define the 2 norm. All right. It's going to be, which in his more obnoxious notation looks like this, L2 RD. All right. This is equal to the square root of the integral, in the Lebesgue sense, of the absolute value of f of x squared dx. All right. Now, of course, you know, if we were to write f equals to u plus iv, what this really looks like is the square root of the integral over rd of what? U squared plus v squared dx, right? I mean, that's what's actually going on here. But this will reduce to just the plain old just the plain old square. Like if we're working in a real valued function, right? If we were working with a real valued function, it's just the integral of the square of the function. That's the 2 norm. Well, the square root of that's the 2 norm. All right. And he says the crucial difference between this, all right, so this being less than infinity, what does that mean? It's square integrable, right? But that means that f is an element of this mysterious new L2 RD, right? AKA square integrable, which is a reasonable enough term, right? Because the square is integrable. Square integrable function. Square integrable functions. Now, yeah, I think more generally LP space is f an element of LP RD, which I really don't have anything much to say about except for this. Then the p norm is the pth root of the integral of the pth power of f, like so, yeah. Such things are of interest, in fact, yeah. That's a definition, yeah. If that integral, if that expression exists and is finite, then f is an element. I mean, I need a condition, right? That has to be less than infinity. Okay, so the main difference, though, between L1, you know, what were these called? What would we call those functions, other than space of L1 integrable functions? Okay. I guess he just calls it integrable functions, right? Yeah. So this is just this is what makes the function integrable in the Lebesgue sense. Very good. So there's just plain integrable. This is square integrable, or whatever. I know that I can say f is an element of LP, as people usually say these things out loud. I don't know what I would say. I don't know how I would complete the sentence in analogy to f is square integrable versus f is p integrable. I don't know. I'm not sure what you say there. I'll be honest. Okay, so one crucial difference is that this L2 has an inner product, actually. And so the inner product, in the sense of complex vector spaces, works like this. Fg equal to integral over Rd of f of x complex conjugate of g dx. Whenever f and g are square integrable. And okay, so once you have an inner, when I say it has an inner product, I mean there's an inner product which induces the norm. And so what do I mean, inner product which induces the norm? Here, if we look at the square root of ff, right? What's that equal to? But that is nothing more than that, right? Which is the 2 norm of F. Now you can ask the question, does there exist some concept of inner product, right? Does there exist some concept of inner product in L1RD such that the norm on L1RD is the induced norm from that inner product for L1? Like, does there exist some inner product for L1RD such that the same thing happens? And the answer is no. So this is a good homework exercise in some class you'll probably take. But I sometimes assign this in like advanced calculus in the finite dimensional context. There's something called a polarization identity, and there's a particular way that you can build, there's a particular way you can take the norm and build an inner product using this set of identities that's known. And that falls down in the case of the 1 norm, even in finite dimensions. I'm not sure what the reason is in infinite dimensions right offhand, but what's that? It's the same algebra, same polarization identity. Let's see here. So what are the properties of, some properties here? So properties of the square integrable functions. The first point is if you add 2 together or you multiply by a number, complex number, you get back where you started. So L2RD is a vector space, complex vector space, in fact. And 2, the product, so if we have F and G in L2, that implies that FG bar is also an element of L2. All right. So the product, well, not the, well, I think it's also true that if, we could say more. We could say that if F is square integrable, then the conjugate of F is square integrable, because in fact the absolute value of F and its conjugate are the same. So that's not even a theorem. That's just like duh, right? So like F square integrable implies that F bar is square integrable, but also the product of F and the conjugate of G is square integrable. And more interestingly, we get the Cauchy-Schwarz identity, which you might recognize from Calc 3, perhaps. So that says norm of F, the absolute value of the inner product of F and G is less than or equal to the products of the norms, 2 norms of F and G. All right. So this is the Cauchy-Schwarz inequality. And 3, F maps to FG linear. And G, well, that's kind of a funny way to say it, but right. FG is equal to GF conjugate. I don't know, have you guys studied complex inner products before? Like inner product in a complex vector space at all? No? I do in my linear algebra, but they may or may not remember, or may or not. Some semesters I like downplay it more than others too, but did you have linear with me? You did. So do you remember me? Maybe not. I'll do a simple finite dimensional example. If we work with C2, so they'd be complex 2 vectors, you know? so the inner product on this thing, if you did say inner product of z and w, it's defined to be z1 w1 conjugate plus z2 w2 conjugate. So it's not bilinear, it's what's called sesquilinear, because it has the following properties. If we had, z plus w u, it's got, so it's additive in the first spot, but you can see what happens here if I switch the order of things, right? Well, if I take the complex conjugate of the whole thing, I could rewrite this as w1 z1 bar plus w2 z2 bar using properties of complex conjugation. So what I did was I took the complex to give you the backstory here, I took the complex conjugate of the complex conjugate, which is not doing anything, and I used properties of conjugation to do that. And then this complex conjugates to that, and this complex conjugates to that. They're numbers, so they commute. And so after the dust settles here, you've got the inner product of W and Z complex conjugated. The real kind of thing that weirds you out when you're used to real inner products is that when you pull constants out of the second component, you pull out complex conjugate like that. So that's the main weird feature of a complex inner product versus real inner product is they're not symmetric, they're conjugate symmetric, whatever you want to call that. And you pull complex conjugates out of the second component. But otherwise, they're a lot like real inner products, right? So the point is to say that all of the standard, just like this inner product on C2, the standard inner product on C2, all of the requisite inner product properties are apparent and ready to derive in this alleged inner product on L2. Because you've got linearity in the first component. If you put a constant into the second component with the G, when you pull out the constant times C, you'll pull out a C bar. It's also additive in the second component, even though it's not, homogeneous in the complex. Anyway, so it is an inner product, is my point. All right, let me move along here. There is also, what else do we got? Part 4, triangle inequality. I've lost my, oh, there it is. All right, so, and then he proves these in gory detail on page 158. And the probably the most exciting thing there is the Cauchy-Schwarz inequality, which is always a little bit cantankerous to prove. And once you have that, the pretty much standard argument gives you the triangle inequality. All right. And then we get to the big theorem here, 1.2, on page 159. And what is that theorem? The space L2 RD is complete in its metric. And what is that metric? I'll call it D2. D2 of xy would be what? Oh, FG rather. It would be the 2 norm of, what did I say? F minus G, right? So just like we did for the 1 norm, we can induce a distance function, and this space L2 is also complete with respect to this metric. as he points out again, this theorem, which is in sharp contrast to the situation for Riemann integrable functions, is a graphic illustration of the usefulness of Lebes's theory of integration. All right. Theorem 1.3, and now it starts to get a little bit more. I don't think this is true for L1, what I'm about to say. The space, although I'm not sure about that. I don't know. You tell me. Maybe you know. Maybe you've done enough reading, Kang. You might know. The space L2 RD is separable in the sense there exists a countable collection F sub k of elements in L2 RD such that what? Such that their finite linear combinations are dense. All right. He doesn't say that it's not the case for L1. Maybe that's already obvious if I've read this book more carefully. I don't know. That's a question I would ask if I was taking a course in this that was more careful. Is L1 separable in this sense as well? My guess is no. Okay, so Hilbert space. What's Hilbert space? Well, the point of talking about these square integrable functions is that they're the sort of quintessential example of a Hilbert space. All right? These give us an example of a Hilbert space. What is a Hilbert space? Here it is. Definition. A set H is a Hilbert space if you have the following bells and whistles. Number one, H is a vector space. Over the complex numbers. 2, it's equipped inner product. Such that, well, the property I was just telling you about, right? So like number one, the mapping F, this mapping with G held fixed is linear. I mean, C linear, of course, right? FG is conjugate symmetric like this. And also, the inner product of F and F is greater than or equal to 0 for all F and H. Now, be careful with this. That last bullet point is a little bit disconcerting because, I mean, if I talked about this inner product more properly, I would tell you it's a function from H cross H into the complex numbers. You know? And so when I tell you that the inner product is a product from pairs of vectors in your Hilbert space to the complex numbers, and then I write an inequality for this complex number, it's a bit disconcerting, isn't it? So there's a little bit there's an assumption built into that third bullet point, right? Is that makes sense, right? I mean, this is actually saying a lot, isn't it? It's saying that the inner product of a vector with itself is a real number. Otherwise, you can't write an inequality about it, right? And more than that, it's a non-negative real number. And you can derive from these axioms that if it's 0, it must be that it's the 0 vector. That's a consequence of the linearity and the other things here. And here's where he starts to get a little squirrely. Oh, well, this is fine. Nothing squirrely here. We let... I don't know how squirrely it is. Sometimes people make a self-serving definition in a book to avoid a larger discussion. And that doesn't seem to be his ninja way, generally speaking, in this book. These books, But I don't know. Maybe I just don't know enough to know that I'm being lied to. The best lies are the ones you believe. If and only if f equals to 0. Just kidding, don't believe lies. Let's see here. But if you don't know it's a lie, I don't know. It's hard advice to take. 4, it's not, and we're still not to the part I'm a little bit, I don't know, I don't like what he says. The Cauchy-Schwarz and triangle inequalities hold. Oh, that's not, there's no double bars here. This is just absolute value. And by absolute value, I mean in the complex sense. Oh, I mean like the absolute value of 2 plus 3i is the square root of 2 squared plus 3 squared. Very reasonable question. Let's see here. Triangle inequality. Cauchy-Schwarz. What else? Complete. H is complete. With respect to metric d fg equals norm of f minus g. And then here's the one he's a little bit squirrely about, because he says that there are examples where this is not the case, I think, but it's part of the definition. So I'm like, what? So maybe this is up for grabs, depending on what you look at, but separable. H is separable. He says, we make 2 comments about the definition of Hilbert space. First, the Cauchy-Schwarz and triangle inequalities are in fact easy consequences of the assumptions in part 1 and 2. Fine. And second, we make the requirement that H be separable because that is the case in most applications encountered. That is not to say that there are no interesting non-separable examples. And one such example is described in problem 2. Okay, so but maybe we should just call that an inseparable Hilbert space or something. All right. I think that, anyway, that's the viewpoint of the book, and that's the viewpoint I'm taking today. All right. So what are examples of Hilbert spaces? Euclidean space? But it has to be complex. Oh, complex Euclidean space, huh? Let's see here. What's that? Oh, like Cn? I guess we could do, you could do Cn, which you could think of as R2d, I suppose, right? The inner product is, oh, no. That's an interesting point, but Cn we can look at as R2n. If you look at the norm in the usual sense of Cn of a vector of complex things over here, it's the norm of Z1 squared plus the norm of the second, I mean, the absolute value of the second component squared, the absolute value of the nth component squared, right? But if you look at this instead as, so this is the Cn, right? But if you look at that z instead as x vector plus, you know, I vector, that being the same z, then that's, well, and I'm squaring it, of course. Then the, you know, the usual Euclidean 2 norm, it's got your x1 squared plus, you know, y1 squared plus x2 squared. Because, well, the thing is, the question is how you make this equality, right? I mean, how do you make that identification? But my point is if you make it in the natural way, namely just by fine. So if the mapping is z vector maps to real part of z vector, comma imaginary part of z vector, like that. If that's the correspondence between Cn and R2n, then if you use the usual Euclidean norm on this thing, you know, and look at the, it's equal to the, because, I mean, that is, in my current notation, so most naturally that would be x1 squared plus x2 squared plus xn squared plus y1 squared plus y2 squared plus dot dot plus yn squared, which of course you could rearrange to be x1 squared plus y1 squared xn n squared plus yn squared, which of course is. So in fact, the natural notion of distance transfers through this correspondence. I mean, it's, that's right, only for even dimensions, I suppose technically. But anyway, this is of course not the interesting case. These are, of course, a finite dimensional Hilbert space, right? And where it gets interesting is the fact that things don't have to be finite dimensional here, and we have lots of interesting infinite dimensional examples. So his example, I think this was example 2. I just erased example 1. Example 1 was the one I've been talking about. The square integrable functions was example 1 of Hilbert space. Example 3 is what he calls L2, L2z. L2z is, it's the set of sort of doubly infinite sequences. They got no start, they got no beginning, they got no ending. If you were at the Math Select Convo today, you might expect me to say something deeper about this, but I won't. Partly because some of you were not at the Convo where you won awards. You know who you are. Let's see here. I realized this morning as I thought about, oh, I didn't say anything to you about this being next Monday, last Friday, because I forgot about it. I thought, there's no chance. There's no chance he'll be here. There's no way. And I'm very envious. I'm very envious. Like, I don't know. In some sense, I very much support your decision. Let's see here. But it may not be actually a decision. I don't know. I don't know why the A sub I and C is so far up there, but sorry about that. But this is L2Z. There's also L2N, which would be, you know, and so forth and so on, such that AI and C and the sum n equals 1 to infinity of the absolute value of A sub I squared. And that was supposed to be an I, sorry. Or this is supposed to be an N. I don't know, you pick it. Anyway, I should have my index of summation matching my, you know, formula. This is L2Z, L2N. And so what are these? I'm not sure what to call these, but these are square summable sequences. What's he call L2Z? Does he have words? He says, we leave the proof that L2Z is a Hilbert space as exercise 4. I guess you might wonder, first of all, what's the inner product on L2Z or L2N? Right, if it's a Hilbert space, it's supposed to have an inner product. I told you the norm. What's the inner product? Let's see here. If I take sequence A and sequence B, and I ask, what's the inner product of A and B? Can you tell me? Sum n equals 1 to infinity of, what do you say, an? A conjugate of bn. We need that conjugate to get the usual song and dance here for a complex inner product. But yeah, that's the inner product on L2. It seems to me like a lot of functional analysis classes spend a lot of time belaboring the details and quirks of L2, like L1 and L2. At least it was that way when I was in graduate school. I vaguely remember my brother asking me questions about these things and me going, I don't know. I like calculus. I don't care about your convergent or divergence. Don't ask me for an example of a divergent sequence. I just want to do math, not that, whatever that is. I was a very bad student as an undergraduate, very bad. Anyway, these are Hilbert spaces. Now, I think the reason one of the big reasons Hilbert spaces are so interesting is that we do have a lot we can say about orthogonality, even though it's an infinite dimensional context. In general, it's hard to say things about orthogonal sets in infinite dimensions because it's just not as nice. Like finite dimensional orthogonal complements, if I tell you you're working in a 10-dimensional space, right? And I tell you you have a 3-dimensional subspace, right? And then I say, what's the dimension of its orthogonal complement? You should be able to tell me 10 minus 3, 7. There's a 7-dimensional perpendicular space if my backdrop is like 10-dimensional, right? Or in calculus 3, if we have a normal, which is 1-dimensional, right? 3 dimensions, so 3 minus 1 is 2. The orthogonal complement to a 1-dimensional space is 2-dimensional in R3, right? In R4, if you had a normal, you'd have a hypervolume, you'd have a 3-dimensional orthogonal complement. But, you know, what if you're working in an infinite dimensional space and I ask you to try to say something coherent about the perpendicular set to a given subspace? You know, is it still true that the perp of the perp is the set again, or is it bigger? Or what happens to that, you know? What happens to the orthogonal complement theory for infinite dimensional vector spaces is something that requires thinking. Some things you keep and some things you lose, and I'll just leave it at that. But here, we can talk about orthogonality in Hilbert spaces because it's not that bad. We have some actually very nice theorems here. And so, first of all, the definition, f and g, if it's equal to 0, that's what we mean f perpendicular to g. So the inner product of f and g being 0 means they're perpendicular. Right off the bat, you've got sort of the Pythagorean theorem. If f is perpendicular to g, then the norm of f plus g is norm of f squared plus the norm of g squared, right? This is a proof I will do today because it's just that easy. Also, this was on my linear test this morning, so it gives me joy. Right? Definition. Then, of course, this is by additivity of the first slot. But then you can complex conjugate, like so, right? And so I mean, if we were spending more time, I would have derived additivity in the second slot and just used it. But since I'm trying to give you a self-contained argument at the moment. But again, you can play this game and conjugate this, right? So like I'll just do it with my marker. I'm going to erase, I'm going to put this in here, and in so doing, I'm going to flippity-flop these. Dang it, why did I do that? That's the one I like. I like this one. We already know that's 0. It's this one I got to mess with. Right? So we're given, I'm assuming this, right? Which is to say that that's 0. So 0, 0, and ff plus gg, which is as you can see, it's nothing about finite dimensions here at all, right? It's just about the algebraic structure of the inner product as it interrelates to the norm, you know? So there you go. This actually was, I mean, not in the complex sense, but I asked this, I think, for a real inner product space on the test today in linear. I'm sure they all got it right because I have not looked at them yet. It's here, even a little. So I can say that kind of thing. That's not true. I've taught linear too much. I really don't find it credible. Let's see here. Actually, do you guys care to guess what? This is a fun game. What percentage of my linear class is going to get the Pythagorean? It's for abstract real inner product space with inner product Langle-Wrangle. Show that, you know, if you have orthogonal vectors v and w, that the length of v plus w squared is equal to the length of v squared plus the length of w squared. What do you think? I got 20 students, maybe 19 students taking the test. How many are going to get it right? Care to make a wager? Let's make it interesting. 12? Wow, optimist. Very optimistic. I like this. 12. We shall see. We shall see. Is it a good linear class? I like linear. Linear is a very interesting subject. It's always a good linear class. A finite, I should always answer that question. A finite countably infinite subset, a finite or countably infinite, E1, E2, dot, 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 of a Hilbert space is orthonormal if the inner product of EK, EL is equal to Kronecker delta KL, which of course is 1 if K equals L, and it's 0 if K is not equal to L. Right? He says, in other words, each EK has unit norm, and it's orthogonal to EL whenever they're not the same one. And then we have the following beautiful theorem. If we have hopefully I picked up a marker that works. Let's see here. Proposition 2.2. Wait a minute, what did I say? Whew, goodness. If we have EK, K equals 1 to infinity, is orthonormal, and F equals to the sum AK EK in H, where the sum is finite, all right, then the norm of F squared is simply the sum of the coefficients squared. So what he's saying is that the thing I just worked out for two things equally well extends for a finite collection of orthogonal things. So the set of all possible orthogonal vectors is infinite, but he's taking a finite linear combination of those at the moment. All right, so it's a finite sum, and so that's just you could easily prove that by induction on the theorem I did do. And he says, given an orthonormal subset of H, a natural problem is to determine whether the subset spans all of H. That is, whether finite linear combinations of elements in the orthonormal basis are dense in H. In this case, we say that that is an orthonormal basis for H. If we are in the presence of an orthonormal basis, we might expect that any F takes the form. So the question is what he means by that terminology, dense, right? E1, E2, da 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 da, orthonormal. Orthonormal in H such that so what would that mean to say that the finite linear combinations are dense in H? With respect to the yeah, so I think what he's meaning is that we can write F in H as F equals to a sum